Hello and welcome to another NX tutorial. Today I want to model some welds and then use the NX motion and pre-pose to validate the design. So first let's design the welds. First let me turn off the ground, and I'm going to use Weld Assistant because I have a fillet which is easier here. Also, I'm going to use the standard that we have here and the course materials, and on the charts you can find this chart that specifies the minimum size of a fillet weld relative to the thickness of the thinnest parent material. Here the parent material is around 100 millimeters, so bigger than 20 the minimum size is 8. I'm gonna go with 20, 5 times less than the thickness of the plate. Then if it didn't work, we can go back and change the weld size. So here we go with 20 and make the welds. I'm also using a triangle cross section because it's faster to simulate, but you can use a concave shape if you want a more accurate result. Same welding for the second connection. And the welding is done, the weld modeling. So we can save here and move to the motion application. But let me turn on the ground again because we need the ground in a motion too. Also, I need to change the appearance a little bit so it looks a little bit different. Here in the motion, I will make a new simulation. I don't need the joint result, and I want the component-based simulation. I want to use Recordine as a solver, and then first motion body I want to make is the ground, so get it out of the way. This is also fixed, so we have our ground. Now I can hide it and focus on the rest of the motion bodies. I want to have a very basic movement. I want to lift the excavator by itself. So we're gonna push the bucket to the ground and lift the front of the excavator to apply some load, to at least make sure that the excavator can lift itself. And to do that, most of the parts don't need to move. So it makes sense to put all those parts in one motion body. So I start from down here and put everything that needs to act as a rigid body in one motion body. So all the stuff down here, I don't want them to move. I'll add them. This is stuff, the motor and gears and other stuff there. They don't weigh that much, so I don't add them to the simulation. It makes the simulation faster. And as I move, I hide so I see the rest of the remaining parts. Now the flexible part is going to be this part plus this part and the weld, which is now in the assembly level. So that's going to be the mesh. So we will put that in one motion body. Then I can also put this one in one motion body and mesh it separately, but this one is harder to mesh. So I will use a point just to fix it. And then the mesh is also will get the load by just a point. You will see that during the modeling. But let's move on making other motion bodies. These parts are going to be in one motion body, and then we have the cabin. There is a problem with the material, but that's not a problem. Probably because of the glass and everything else. We can move on. The rest of the stuff around here can move together. I'm only selecting them because of the weight they add to the structure, so they should be selected. Also this part and this part and the pins as well. Except these parts, they will push the bucket up, the bucket and the rest of the parts that are selected. Let's apply. I left this fixed checked, so we have to go back and uncheck that later. The only part we needed to be fixed is the ground. And then we have this is acting as one part. We probably need to add this one later. And then we have this part which is acting. But let's first finish the, let me go back and finish the piston and cylinder on this side, then we can do it on that side. On this side we also have a cylinder and a piston. So let's go back and fix the joints that we made. I mean unfix somehow. These are correct. Our main parts. And as I said, we can hide them, and we have a face on the assembly level which is used for welding. It doesn't matter, it can be here, but it won't participate in any of the motion simulation. Anything you don't add to motion bodies won't affect your simulation. We have the cabin here. So this part in the top needs to be here. Let me add it again. This part can't be selected because it's probably a sub-assembly. We can go back to the model and bring it up to the assembly level, and then we can add it to a motion body. But it doesn't matter for now, we can just hide it. Doesn't weigh that much. And we can use higher safety factors because we are removing some of the parts that may weigh something. And then that part is okay. The piston on this side, the cylinder, and cylinder and piston on the other side, and we should get one joint only. So this one is also fixed. We need to unfix it. And we have only one joint, which is for the ground. We can save here. And then we can move on to make the joint here, which we need, and here, and make a slider. First, the joint. We'll move to the joints. I want to have two joints on this piston and cylinder. The revolute joint. At this point, since we are not interested in the stress on this pin, we don't care about the exact location of the revolute pin, but we are more interested in the forces and stresses on the weld. So here I just need revolute joints. Let's select the vector as this. And the motion body and the base will be this one. Same for the other side. I want to connect this motion body with the revolute on this cylinder and the vector on the cylinder, and with the base, which is this one. Same for here. I want to have this motion body, the origin should be here with the vector of same, and this is the base. The last one, the origin and the vector with the base of like that. Let me make these joints a little bit bigger so it's more visible. Let's go with 100. Yeah. Okay, we have the joints, and now we need the slider joint here. I'm gonna use slider. The first motion body is the piston. The origin I want to be around this cylinder, and the vector should be in line with the piston, and the cylinder is the base body. And we're gonna have similar thing for the other side. We want this to slide with the origin around this point and toward the piston itself with the motion body of the cylinder. Let me make it bigger, and here is the slider. Now let's bring back the ground. I want to define contact between the wheels and the bucket and the ground. So when I push the bucket to the ground, I will lift the wheels. So let's define the contact. The bucket and the ground. The rest of the excavator and the ground. And it will be represented by these lines that show the contact. Let me save here. And I need to drive this down, so I'm gonna try. Since I don't have any signal chart to drive it, I can just drive it on the joint itself. And I want it to drive by, let's say 100 millimeters. Probably should be negative, but I'm gonna check it later. Now let's check the environment. We have dynamics. We don't have any motors, but we want to have flexible bodies. I don't want any co-simulations with this one, and we can move on to the solution. It's a flexible body. The gravity is this way, which is correct. I didn't check the control dynamics, so I go with kinematics dynamics. I don't need any control in this simulation. So let's run the simulation and see the reaction. You have a couple of redundant constraints which will be removed automatically from the simulation. So we forgot the main joint between the body. Let me play it again. The first animation you play is a good way to find out the problems that you have or the connections that you forgot to have in your simulation. So let's see. There should be connection between these two bodies. So three connections are missing. Let's go back and fix it. We're gonna have a revolute joint between this motion body and this one as a base. The origin I want to be at this point with this vector. Let's run the simulation again. Let's play the results. We're missing the connection between the cabin, also the main pin here. So let's go back and fix that. First, let's fix the cabin joint. I can fix it by using a fixed but you need to be careful about the origin that you select, because this origin point should match exactly what you have in the finite element. That's where the load will be applied. So I will change the origin to somewhere known, like a point around here, maybe at the corner. That will apply all of the load to the corner, but we could select any points. But this is the reference that I already have here. This one. So that one is fixed. And let me hide this one. So we have the joint here. And now we need the cylindrical, sorry, the revolute joint here. Between this motion body and this as a base on the origin of, the origin is correct, but I'm gonna reselect. The vector should be corrected and the base is okay. Let's bring back the cabin, save and run the simulation again. We probably have a problem with the cabin, so I'm gonna turn on and off the, yeah, the problem is here actually, which we defined fixed joint instead of revolute. Just go back and change it to revolute and solve. Okay, so let's see the results. As you can see, I have contact only between one wheel and the ground. So I'm gonna go ahead and define contact between the other wheels as well. Between this one and the ground. This and ground, and the final contact we want to have is here and here. Now let's solve the simulation. And let's see the results. As you can see, the contact is really stiff, it's bouncing up and down. So I'm going to relax the contact a little bit. Also that 100 millimeters wasn't enough, was too fast, so it's not a good idea to move by initial displacement. Let's specify a velocity of, let's say, minus 100. Let's solve and see. Simulation is finished. Let's see the results. Damping is, I guess, too much and we don't get any contact. So after a couple of iterations, I found the best contact parameters for the simulations. It should be a little bit stiff so the parts are not going inside each other because it's heavy. That's why I need a lot of damping. But the more important parameters are the resolutions, which you can see I reduced the buffer length. So the resolution is going to be higher. And it takes a lot more time to simulate, but it converges to something that is more acceptable. So We have some shakes at the beginning, but that's okay. And the rest of the simulation seems good. Again, the parts like this that we don't need inside the simulation can be like that, it's okay. So the motion seems good, and now we can go to the pre-pose, make this part flexible, and then come back and run the simulation again. Now, before we move on to the pre-pose, let's make sure about the contact points of the flexible body because they need to match what we have here. Our contact points are these revolute joints here, and then whatever that is holding the cabin. So I'm going through the joints. This one seems to be what we are looking for. I'm going to scale it up to improve the visibility. And then probably this one, which is fixing the cabin. And let's see if that we have a central one as well that should match with the flexible body, and then we have the rest of the joints. So here we only have this one, which we need to define another joint here to make two contact points to the flexible body. So let's define a new joint of revolute type. Here the origin is very important because it needs to match the flexible body. I'm gonna use the between 2 points to get the exact location between these two ends. And for each point I can use the arc to capture the point in between. And the vector can be like this. So we make a point when we are meshing the flexible body, then that point will match this one, and that works as a transferring load point. Let me also scale this up so we have a better view. And also I need to fix the other joint here, joint number 10. I only need to fix the origin to be in between the parts. Vector and everything else is okay. Here we use the different base and motion body. It seems that, yeah, but it's okay. And I will run the simulation in motion one more time, and then we move to the pre-post. Let's take a look on the results. Results seems okay, so we can move to the pre-post now. To move to the pre-post, we have to go back and select the main assembly, and then we can take that assembly part to the pre-post. So I will first open the assembly in a new window. We could only open the parts that we need, but we can do that when we are selecting the parts for doing the pre-post. Okay, now on the pre-post, we can select the flexible bodies that we want to bring in to the finite element method. I'm going to make a new finite element method. Instead of all visible, I'm going to go with select and then select the bodies that will act as flexible. So these are the parts that I want to convert actually to flexible bodies inside the motion simulation. So I select all the parts and solver should be on SimCenter Nastran. Click OK. And then on the solution, we need to select flexible body, create the solution. Here we need to change the export file, which is record done. Also on eigenvalues, it's good if we take a look on the frequencies. It usually starts around 0 as the lower limit, but just to capture all kinds of deformations, I'm gonna go from 0 here and find up to 20 different modes. So hopefully cover of the possible deformation of this body. The rest of the options are okay, so we can continue. And now we can start meshing. Now we have a lot of different details that require different size of the mesh. For example, this box here, we don't need a big size of mesh. We don't need a small size of mesh for this one. We don't need details. We just need to connect it to the main body. So I will start with tetrahedral because we also have holes that will make a better mesh. I stick with larger size like 400 or even 500. The recommendation is 38 because of the small details here, but we're going to go with bigger size and then change that to the small body. But it will automatically ask the size is big for the highlighted geometry, and we can click yes to switch that to the smaller size. So the size of the mesh is going to be something between 500 and some smaller size like this, around 30, based on the size of each body. So this is the mesh for different parts, but parts are not, meshes on parts are not connected yet. So we go with mesh mating, and I want everything to be connected together, so I select everything. The distance seems good, and I click OK. we had 27 faces that are now connected to each other. But it still doesn't show it here because you need to update the mesh. So I'm gonna keep it around here so you will see what happens after the update. Now you see that near the places that we needed mating, the elements are aligned to share a node, so the mesh can mate on each face. And also the size remains big for the parts that we don't need much detail, but it's getting small around the weld. This mesh seems okay, except at this point we can go with the mesh control and we can go with chordal tolerance, so it will automatically base the mesh size on the tolerance of each edge. Let's go with higher values and check what happens. This is the number of elements that we're going to get around here. Let's go with a bit lower. This seems fine. And now we can update the mesh. Okay, so we got enough elements around that hole, so it seems fine now. Also on the other side, it seems okay, even though we are not interested in the stress on this point, but it will affect the stress distribution because it's near the well. Now we can move on to make points for transferring load or transferring motion or contact. Let's go with the first here. We can start by the pin that we have here. So I will go with point to face. The points I had in the motion simulation was between point. I'm going to go with the same thing. Here we have between 2 points and we selected the elliptic or arc for both on this side and this side. So this point matches the point that we defined the revolute joint. And I want the load on this point, which is coming from the revolute, being transferred to the face here and here. Now if I just see the results, we're gonna see a kind of a spider that is transferring the load with rigid body element, which is what we actually want. So this is going to be the first one. The second one is exactly the same for our revolute joint. I will select between 2 points, one arc here. The faces are here and here. Then we have another point here which is connected to the cabin, and then we have two more here which are connected to the pin. So since we are still on the point to face, let's do this first, then we move to the cabin. Between 2 points. Now this should be here actually. And the faces are here and here. I think we need to fix the revolute joint because I'm not sure if we defined the revolute joint at this point, but we can fix it to match. Yeah, between 2 points. And then I can transfer the load of the cabin from point to face, or point to face would be a good option. I can transfer this point to these two faces on the side. Let's see the result. This is going to be how the load is being transferred. Or we could go with these two faces, like this point and then point to face, this point, and these two faces to make more sense. Let's see the result. Yeah, this seems a better option. We can add this face too. Okay, now we have also another spider here to transfer the load of the cabin at this point. Before we move on, we need to assign materials. So I'll go back to the FEM and I should assign a steel here. And then we go back to the simulation side and assign the constraint, fixing the boundaries because we want this flexible body to be fixed on the motion body. Make sure you select only the points. I have one fixed here, another one here, and then here. And we can move on and solve the problem. The simulation is finished without any errors, and let's take a look at the results. The shape modes are now generated. It should start with very low frequency, which are usually the main movements. Let's animate it. So the basic movements up to the more complicated shape functions. And higher frequencies. Some weird shapes. Yep. So let's go back and plug this in into the motion body. We save here and then go to the motion. But I first need to go back to the part file and to the motion. we should actually select the motion from here, which is this one, and then go up to the motion. Yes, so we are back on the motion, and now we can plug in the flexible body instead of the main body we had there, B002. Now we can make this body as flexible, and here I need to add this RFL file. Let's go with absolute origin, which fits good. I only need to check the connections and we're good to go. All connections are okay except one, which is probably one of the pins here. I can also hide the ground and this body that is now flexible. So let's solve and see what's happening. Now the simulation is finished and I can check the result. The best way is to just jump to the last time step instead of playing it, because this model is really large, so it takes a lot of time to show the animation in real time. So this is how the stress looks like. You need to go to the post view and change. It's usually on the displacement nodal magnitude. So your model looks something like this. So you have to go here and change the result type to a stress nodal or elemental. I'm looking for nodal von Mises. And we don't need to combine the stresses to smooth it, and we can see how the results look like. The maximum stress is around 80 megapascal, but of course we need to read the results at different points and different elements by using hotspot method or other method.